Physical and chemical properties of hydrocarbons. And we're going to talk about the property of alkanes for just a second. And you remember that alkanes are made only out of carbon and hydrogen, and their generic formula is CnH2n plus 2. They're saturated hydrocarbons, meaning they have the maximum amount of hydrogens possible for every carbon. And so, because alkanes are composed of nonpolar carbon-carbon and carbon-hydrogen bonds, they are nonpolar molecules and therefore insoluble in water. So again, what they're saying here is when you have an alkane, okay, a hydrocarbon, an alkane, the only possible bonds you could ever find in an alkane would either be a carbon-carbon bond or a carbon-hydrogen bond. Neither of those bonds are polar, and therefore, if the molecules are made out of nonpolar bonds, then they have to be nonpolar molecules, and therefore, they're going to be insoluble in water, right? Because water is a polar molecule. Now, alkanes have lower melting points and boiling points than other organic compounds of comparable molar mass or molecular weight because they only exert very weak intermolecular forces or attractions between each other. And the only intermolecular force you're going to find between two hydrocarbons are going to be London dispersion forces, which are very weak intermolecular forces. However, when we go from methane to ethane to propane to butane to pentane to hexane to heptane to octane to nonane to decane, as the number of carbons in our chain increases as we go from 1 to 2 to 3 to 4, so on and so forth, the melting points are going to get higher, and you're going to see that the boiling points are going to get higher as well. So the boiling points are going to increase. Why? Because the London dispersion forces are additive. Now, before we go on and we take a look at a chart that shows you the trends that are described here, I want to cover this word with you, hydrophobic, okay? It shouldn't be hydrophobic, it should be hydrophobic, and yeah, it's a mistake in the slide, but hydro means water, right? And phobic would be like it's something you have a phobia of, so it would be water hating or water disliking. And so hydrophobic molecules are going to be parts of molecules or molecules in their entirety that repel water. And so alkanes are hydrophobic molecules, right? If they're nonpolar, then they're going to repel water. And so here's a chart that compares or shows the first 10 straight chain hydrocarbons. So we go from methane to ethane to propane to butane to pentane to hexane to hectane to octane to nonane to decane. You should know the names and know that they contain 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 carbons respectively. You should be able to draw the condensed structures that are shown here. You should be able to draw the bond line structures. There's no bond line structure for methane, but for ethane, it would just be two carbons attached like this. For propane, it would look like this, 1, 2, 3. For butane, we have 1, 2, 3, 4. For pentane, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. For hexane, 7 for heptane, so on and so forth. And the only trend I'm really going to draw your attention to here is you notice that as the chains get longer, as we go down this group of molecules from 1 to 2 to 3 carbons all the way up to 10 carbons, you'll notice that the boiling points get higher and higher. You also notice the melting points get higher and higher as well. But anyhow, I just want to focus on the boiling points. So you see that the boiling points of methane, ethane, propane, and butane are all less than 0. So that means that all of these are gases at room temperature. Whereas once we get to pentane, hexane, heptane, octane, nonane, and decane, these are going to be liquids, right? Those would be liquids at room temperature. I'll just use RT. And so the reason why is because the longer the chain is, the more London dispersion forces you're going to have between two molecules, and therefore we're going to have higher melting points and higher boiling points. And you can see the densities increase as well. The way I describe this to my students sometimes is I'll say, let's say you had two molecules of propane. Okay. Let's say you have a molecule of propane here and another molecule of propane here. Well, there's some surface area between these two of these, and that's going to be our London dispersion forces. However, what if I had something like heptane? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I have two molecules of propane and I have two molecules of heptane, but between my two molecules of heptane, I also have London dispersion forces there as well. The forces are the same, but it's going to take more energy to separate these two molecules because you have an additive effect of the intermolecular forces. It's like if you had a piece of Velcro that was, say, 1 inch long. Let's say you had a piece of Velcro that was 1 inch long, right? It's going to take you some energy to rip that piece of Velcro apart. But let's say you had a piece of Velcro that was 6 inches long, right? It's still the same Velcro force holding the two pieces of Velcro together, but it's going to take you more energy to pull it apart. And so that's the rationale I kind of use for hydrocarbons. As the chain gets longer, it's the same force, it's the same London dispersion forces, but again, they're additive. So if the chain is longer, it's going to take more energy to separate the molecules. And therefore, as the chain length increases, we're going to have higher boiling points, higher melting points, and densities increase as well.